So, energy calculation. Energy calculation. And in this case, let us say of a protein. So, this we will discuss now. So, so one way to do using quantum mechanics. Yeah. So, quantum mechanics, have you studied little bit? Start. Yes or no? Quantum mechanics you know little bit, you know? Not much. Little bit. Okay. Another way, classical mechanics. Okay. So, there can be two approaches, right? One is quantum mechanics, one is classical mechanics. And the question is which one to use here, which is more practical, better. Actually, so what is the, I mean, of course, I am not going to teach quantum mechanics now. So, this is another subject, but very basic idea, it considers electrons, right. That is the quantum mechanics. And in the classical mechanics, there is no electron. So, your units are, I mean, atoms. This is one major difference. So, in classical, I mean, quantum mechanics, the smallest unit, smallest particle, electrons, and then you do a lot of calculation to calculate the final energy. So, have you read, I mean, maybe you know this Schrodinger equation? You know this equation? You know, okay, very good. So, in principle, we can use quantum mechanics to calculate energy of a protein, but the problem is it is computationally very expensive, it is very complicated. So, what is used usually is this is the preferred most of the cases. In classical mechanics, of course, when you use classical mechanics, there are no electrons, that you know, right. Classical mechanics is atoms. So, like this one I can represent by classical mechanics, right, but I do not consider what is inside. Of course, it also has electrons, protons, but that I do not consider. But in classical mechanics, your smallest units are atoms. So, for the protein case, generally speaking, this is the preferred approach to calculate energy. Why? Because it is simpler, I mean simpler than quantum mechanics, and it is computationally faster, So, that is why we will discuss the classical mechanics description to calculate energy of the protein in today's class. So, what we will do first, we will draw a peptide. What is peptide in Japanese? Nihongo de peptide. Peptide you know, right? When amino acids, not protein is very big, and peptide is maybe 10 amino acid, 10, 15 or whatever, that is called peptide. Let us look, let us draw a small peptide and just try to understand. I am just putting R here. So, I am putting this is R1, R prime say. So, in this peptide, how many amino acids are present? How many you understand, right? Is it 1 amino acid, 2 amino acids, or 3 amino acids, or 4 amino acids? Can you tell me this? Because actually this is one amino acid, number 1, this is another number 2, and this is. So, it is called tripeptide. Tri means 3. Yeah. Okay, that's not so important. I'll erase this part. But let's calculate energy of this. So, one is that let's consider the bonds. Bonds means like CH, this is one bond, maybe this is another bond. These are bonds, right? Okay. So, you answer me one question, I will ask you, you have to answer. If you change a bond length, you know bond length? Right. So, this is maybe I forgot, something like that maybe, approximately, whatever, yeah. So, if you change the bond length, so this is the bond, so you are changing, you are increasing, stretching, will the energy decrease or increase of the bond? So, you understand the question that if you change the bond length, okay, will the energy increase means this, or decrease? What do you think? Let us say the bond is at its equilibrium position, the best position, then you are changing. So, will the energy will go up or down? What do you think? It will go up, because you are destabilizing. And this is easy to understand. Actually, you can plot something like this because let us say this is the equilibrium bond length, this is energy, and this is R. R is the bond length. Okay. And what happens that if you increase the bond length from its base, this is the base position or equilibrium position or equilibrium. Base or equilibrium position here. Okay. So, if you increase the bond length or decrease it, energy will always increase, because equilibrium means lowest, right. So, that is why I plotted. So, maybe this is a relative, equilibrium means I say energy is 0, but if you increase it or try to shrink it, decrease it, energy will always increase. And so, from this the expression for bond energy expression. So, let us see. Do you know this one? I do not know the Japanese parabola. What is in Japanese? Parabola, this shape. Yeah, because this is a very important shape in circle. Circle, you know, right? This is circle, and this is actually a parabola. I will tell you later. I do not remember the Japanese name, but this is actually a parabola type of, and it has a specific energy expression.